Let's try that again. Good evening, everybody. How's everybody doing? We excited? How was dinner? Excellent. Well, we're going to now pick up back with the programming, and I'd like to welcome the AZCs from Zones 2 and 7 to please come to the stage. Can we get a drum roll while they walk up on stage, please? Thank you.
Good evening. My name is Abigail Ambrose, and I am the Zone 7 Associate Zone Counselor, and I attend the College of Worcester in Worcester, Ohio.
Hi, I am Robert Malikian, the Associate Zone Counselor for Zone 2, and I attend Ithaca College in Ithaca College, New York, or Ithaca, New York. Okay. Our speaker tonight is Dr. John Mather, who won the Nobel Prize in Physics in 2006, accompanied by George F. Smoot for their discovery of the blackbody form and anisotropy of the cosmic microwave background radiation. This work was groundbreaking in its support of the Big Bang Theory and is considered the study that paved the transition of cosmology into a precision science.
As a child, Dr. Mather grew up in a farming community in New Jersey, where his father specialized in research on cattle breeding and feeding, while his mother was a high school French teacher. He discovered from a young age that he loved science, and luckily, his family was supportive of this passion. Once, they even put up with him keeping 8 rats under the kitchen table while feeding them various diets as a science fair project. He received his Bachelor of Science from Swarthmore College with full honors, and his PhD from the University of California, Berkeley.
During his time in university, Dr. Mather found his passion for space.
Dr. Mather has spent his career working as a scientist at NASA, starting his career there as a postdoc. The Cosmic Background Explorer mission, also known as COBE, was launched by NASA in 1989 to measure the microwave background of the observable universe. John Mather was the principal investigator for the far-infrared absolute spectrophotometer and one of the 3 leads from a team of more than 1,000 scientists and engineers. It was Mather's instrument that delivered the groundbreaking blackbody curve of the cosmic microwave background. This determined the background temperature of the cosmos while simultaneously ushering cosmology into a golden age of precision and measurement.
Still at NASA, Dr. Mather has moved on to another paradigm-shifting mission. He is currently the Senior Project Manager Scientist for the James Webb Space Telescope, a project that he says represents the hopes and ambitions of 10,000 astronomers who have already used the Hubble. This mission has the passion of Mather since 1995 and is scheduled to launch in about 2 years. Dr. John Mather is an icon to look up to, not only for his accomplishments, but for the journey that brought him to these accomplishments. Dr. John Mather exemplifies the ideals and goals of the Society of Physics students and Sigma Pi Sigma through his endless dedication to furthering our understanding of the universe, to dutiful and benevolent scholarship, and his commitment to being a lifelong student.
We are incredibly excited to introduce to you Dr. John Mather.
Well, thank you. Yay. All right. So can you hear me in the back? Is this working? Okay. Well, thank you for the lovely introduction, and it reminds me to say that, as a great sports athlete said, there's no I in the word team, but there is an I in the word win. So what I'm telling you about today has been the product of many people over many hundreds of years working out the principles of physics and building the projects that I'm going to tell you about today. So what I'm showing you on the picture here is the great James Webb Space Telescope, as it will be in outer space, except, of course, it's not quite right because you can see it. If the actual thing were in outer space, the mirror would be in the dark. So anyway, it's beautiful. It's gold. The great golden hexagon is 6.5 meters across, which is bigger than the rocket. So we will show you the origami that it takes to put this up in space. This is a project of 3 international space agencies: NASA, the European Space Agency, and the Canadian Space Agency. And we're doing it on behalf of everyone. If you're an astronomer, you will be able to write a proposal to observe your favorite target with this great telescope. So, by the way, the call for proposals will be issued in January, so not far away. So this project is planned for launch in March of 2021. Wish us luck that nothing really terrible happens between now and then, but it is all bolted together into one piece and going through its final stages. So that's the sort of thing I'm currently working on. Now I want to show you a couple of smaller things because, as most of you I think have heard, we've been sponsoring summer interns to come to work on Capitol Hill every summer. And so here I am with last summer's 2 interns, and Gia and Nicholas are both here today, and we're sitting there with Bill Foster, who is a congressman and also a physicist, a particle physicist who worked at the Fermi Lab. So when Bill was running for office, I said, well, he asked me for help, so I said, well, what got you into this? And they told me his story, and I thought, well, I'd like to have more people like Bill in office. How do I get more? And so I said, eventually, let me look for a way, and the Society of Physics Students is the way. So if you want to come and study public policy on Capitol Hill, please apply. So while I'm also working for NASA, of course, let me mention that there are also internships for NASA students, for people to come to work at NASA. If you want to know how, just look it up on the internet these days, which is still a great miracle. And you can apply. There are some deadlines, but do not wait. If you're not a citizen, but you are a legal resident, you can still apply for the ones at Jet Propulsion Lab. And for contractors, of which there are many, many, they have summer internships too. So you can get into the space business without being a citizen sometimes. So as was mentioned in the introduction, I grew up in northern New Jersey. This is where I lived. That's the view from the front yard. And that barn housed 20 gigantic bulls. They were the fathers of 10,000 cows of northern New Jersey, and they didn't know a thing about it. It was also a chemistry lab, but to tell the truth, I was not that interested in cows. I was interested in the sky, and so I've been curious about how did we get here ever since I was a little kid. So some of the things that I'm going to tell you about were already known 2,000 years ago. So how did we get here? Well, Lucretius was working on this question, and he wrote this little poem, and this translation tells you basically the implications of the atomic theory. Why did people think there were atoms 2,000 years ago? Because you could see things evaporate. So how did they evaporate and disappear? Well, they must have turned into tiny invisible particles. So anyway, they thought about this, and this is basically the story that I'm telling you today. How do things grow and cling to each other and then disintegrate? By the way, this also has in the idea of linguistics, because we give names to things and we know things, and then they disappear, but they're still there in their constituent atoms. So now here's my more technical version of how does it work. How did we get here? Well, we certainly know that quantum mechanics describes everything that we see, from the subatomic particle to scales to the largest. And if you really want to know about concrete, it's better to go measure than to compute. We know the universe was very compressed, very hot, and very smooth when it was young, and we've measured information that tells us that. We know that it was unstable, and that's one of my other stories that I like to tell about. Energy has been released by reorganizing that primordial material into complex systems. And so we are here because of that. The universe is extremely large, probably infinite, although I can't prove it to you. And it has been here long enough, so things that seem very unlikely, like the formation of life and human beings, has had obviously time to occur. We have learned about stored information. which enables rather dramatic complexity. If I have a DNA system and a system in my cells that decodes that information, then I am here. I can be able to contribute to the enormously complex life that we now have. Notice I call evolution the survival of the lucky. People used to think when evolution was first recognized that obviously it was proved that we were the top of everything because we were here and we were writing the story. And so obviously evolution was in order to produce people. These days I think that's not so clear. And indeed, it's an even open question, how come are we here and not somebody else like the Neanderthals? Don't know that answer. Another interesting thing is we have learned about engineering. We now know how to make a feedback loop that controls something and stabilizes something. And the biologists have a term for this too. They call it homeostasis. And that explains how come I can be telling you this story even though almost all of my atoms have been replaced. All of the ones except my teeth and probably the nerves in my brain have been replaced many times. But I'm still here. I still remember somewhat what I learned in school, and that's because of homeostasis. These feedback loops do not have guaranteed stability, and so therefore it's all temporary. And the only reason that we think things are stable is we don't live long enough. So a little bit about instability. I think many of you have already studied this question. When does a beam buckle? Because it's been loaded, and it buckles if the amount of elastic energy in the beam when it's bent is less than it would have been if it were just compressed straight. So one of the very first calculable instabilities was worked out over 2 centuries ago. So engineers still need to know this. They tell you how wide your column has to be so that it doesn't break. And even before we had the math, the ancients knew how to calculate how big their stone columns should be. So more recently, not so far back in time, but still over a century ago, James Jeans told us about astronomy. He said, what if I have a cloud of gas way out there in space and it is feeling its own self-gravity? Will it collapse? So he said, yes, it will, if the time that it takes for the sound wave to get across the cloud of gas is longer than the free fall time. Turns out to be equivalent to the statement that the gravitational force of the gas on itself is greater than the pressure holding something up. So you can now calculate right away from this how big does a gas cloud of stuff have to be so that it'll collapse. So this is actually what we see. So here's a picture of a cloud of gas turning into stars, and we see it beautifully with the Hubble Space Telescope. So this is important because it's part of our history, and now I want to show you a little bit more about how that works. So when a gas starts to fall in, it gets heated up. Well, gas getting heated up will resist getting compressed more, so this eventually might stop, except it doesn't. So more stuff falls in, angular momentum is conserved, so it starts to spin up. After a little while, the gas can radiate away some of that heat that it's received from being compressed, and the contraction can continue. So also angular momentum can be expelled back out into space by material flying out. And the upshot is you can make a concentrated object with a star in the middle that has negative gravitational energy and plus some positive kinetic energy and some radiated entropy. So the universe has now found a way to increase entropy by producing concentrated order in the star itself. It's all squeezed together. The upshot of all of this is, in repeated cycles, galaxies form, stars form, planets form, and people are here because of that. So thank you. I'm glad that works. So this brings me to the subject of the different phases of matter. So there are lots of different phases of matter you've heard about. The ancients knew about earth, air, fire, and water, and the various compounds like mud. These days, we've thought about this a lot more, and so phases of matter are described more like, well, we have well over 90 of them in the catalog, different phases of matter than have been recognized. So these happen when large-scale phenomena are very, very different from small-scale phenomena. So maybe we'd have now this lovely little snow crystal here. Doesn't look like the little hexagons you're used to seeing, but I just thought it was fascinating because it tells you conditions matter. Everything doesn't grow into a nice hexagonal snowflake. This is a snowflake too. At any rate, the subject of transitions between these phases has been the subject of at least one Nobel Prize, which is describing the way that order in space changes when you get near the critical point. So with gases, liquids, and solids, the critical point is the spot where it doesn't quite know if it's a gas, a liquid, or a solid. So that's a totally remarkable thing that you can make so many mathematical descriptions of that. I just wanted to draw your attention to it because it leads on to another topic of symmetry. So here is a picture of two people who worked on the relationship between symmetry and conserved quantities. How many people here know what a Lagrangian is? A fair number. Good for you. So there's a difference between the kinetic energy and the potential energy of a system. And so it turns out if you can do something called variational calculus, say, I know what the trajectory of this system is supposed to be. Let me say, what if it went a little bit different? And so if you do this little calculation, you can say, I turn F equals ma into the principle of least action. So integrate this Lagrangian along the path that your system takes, and it gets you a minimum. That turns out to be equivalent to F equals ma. So I think of it as a math trick, but it's turned out to be one of the most important and powerful math tricks we have ever had in physics. And in particular, it was noticed by Emmy Noether back in 1915 that if your Lagrangian's function here is symmetric in some way, then it probably corresponds to something that is conserved, like energy. So she did this in 1915, and as one friend of mine said, it was such important work that Eugene Wigner got the Nobel Prize for it in 1963. Of course, he did something additionally. He worked on the quantum mechanical version, which didn't exist at all in 1915. Nevertheless, one of the most extraordinary principles of science is this Lagrangian business. So practically every book on high energy physics, quantum field theory, and so forth tells you about Lagrangians. Now I want to show you something rather surprising. If you imagine something very ordinary that we can make, it's not so very ordinary. If you take liquid helium and take the rare isotope of liquid helium, helium-3, and cool it down to a very low temperature, about 1 millikelvin, it becomes a superfluid. Well, what happens in a superfluid? Well, you get to do quantum mechanics all over again. And it's called second quantization. It says, let me now consider the acoustic oscillations in this very soft, cold liquid, and those are now describable by quantum mechanics too. And so it turns out, and there's a whole book about this, which you can find, that says if you do this, then you get a system of quasi-particles that look an awful lot like the particles we live with. It's got fermions and bosons. It's a standard model of physics together with Lorentz invariance and everything else. Turns up to be a spontaneous result of this special new substance that we've made on purpose, and we know what it's made out of. It's made out of liquid helium-3 atoms. The equivalent of the speed of light, the maximum speed you can get is about 3 centimeters a second, so it's pretty slow. Nevertheless, you can now study this. It's like having a little universe in the laboratory. So I cannot tell you that it is the universe, but it is awfully darn surprising. And it even has the equivalent of the cosmological constant, which is the surface tension of the droplet of liquid. So there's a hint here, which is that maybe our universe, this quantum mechanical thing with relativity, is an emergent phenomenon on some other substrate, something hidden from us which we may never understand or detect in any way. So I can't say that it's there, I can't say that it's not there, but I think this is an astonishing result. And for those of you that are interested in quantum field theory and the fundamentals of physics, I just wanted to draw this to your attention. Now I want to move to another topic, which is non-equilibrium phenomena. So here I'm showing you a picture of Hurricane Harvey. I like this picture because it describes something that happened to our Webb telescope team. We were testing our telescope in Houston, in the giant vacuum tank in Houston, and the Hurricane Harvey dropped 51 inches of rain on the outside of the building while we were testing our telescope in the vacuum tank inside. But this is an example of a spontaneously occurring heat engine. And it's a sort of fundamental principle that we can use in physics and a lot of other ways to say, well, how does nature organize itself to draw energy from a gradient of some sort and increase entropy by producing an organization. So here's a spinning pattern of air movement drawing heat out of the surface of the ocean, causing this huge wind field to occur and generally upsetting everybody. But it is a naturally occurring heat engine that does that. So there's no particular limit to how complex this could have been. It's usually chaotic. Depends very much on history. The hurricanes are not all the same, but the general phenomenon of having a hurricane we now know is always there. So this is a sort of general description of everything you see around us. Our world is a non-equilibrium system. It is driven by the heat that comes and light that comes in from the sun and that goes back out into space as heat. And so this is a pretty remarkable thing to be thinking about. Non-equilibrium is everything. We study in physics the equilibrium things because we know how to do that. But the ones that are interesting are the non-equilibrium ones. So a couple of principles of physics I've noted here. In quantum mechanics, it's often said, if it's not forbidden, it's required. And that means if there's no selection rule, no symmetry in the quantum mechanics that says something can't happen, it'll turn up, just look harder. But when you look at the systems of people, it's sort of the opposite. If somebody tells you you can't have it, it must be something pretty good, so let's go try to get some. So anyway, non-equilibrium phenomena, very much our world. So some examples about that. Here's the game of Go, illustrated in a picture here. The game of Go is a sort of example of one of the toughest board games ever invented. And so there are a lot of consequences of this unpredictability of our real world. Murphy's Law tells us if something can go wrong, it will. My thesis project, which failed to function properly as a graduate student, says if you do not test it, it will not work. There's an awful lot more ways for something to fail than there are for things to work. It means that astronomy, geology, and biology are all observational sciences because they are all these kinds of chaotic processes given by non-equilibrium and systems drawing complexity out of energy gradients. Exponential growth is always limited, so you see, well, we've got exponential growth of our society these days. We're getting richer and richer and more powerful. Something is likely to happen. I like this little law from Sutton. Willie Sutton robbed banks. And he was quoted as saying, I rob banks because that's where the money is. He said he didn't say that, but everybody thinks he did. So another point here, people have talked a lot about climate change. Here I'm just saying humans as a geological force. We are big enough that in about 1,000 years we can burn up all of the coal that it took nature 60 million years to make. So something will happen, and I don't know what it's going to be. That's an interesting thing, but I would say, as a scientist, we have the job of figuring this out. I want to talk about another thing that's attracted my attention lately, the non-equilibrium phenomenon of life. So you say, why is life so complicated? Well, here's one of the reasons. This is an abstract, or a piece of an abstract from a paper that came out this year about biological systems. So biological systems resemble physical systems in a remarkable way. There's a certain sort of physical systems called glass, where there can be, it's not exactly crystal, it's not exactly ordered, but it has various kinds of long-range orders, and it's tricky. So physicists study this, and they've noticed that there is a parallel in the way that those systems are organized and the way that biological systems are organized, which is to say, there's a competition between the ordering processes on all different physical scales. So that says the little nanobots that make up my cells, they have their own interests at heart, but they're ordered. They're all competing and cooperating in extraordinary biological ways. So there's a way of getting at this mathematically, and I wanted to bring this to your attention just because I was so amazed. Now I want to talk about the history of the universe and what you thought I was going to talk about. So a series of fortunate catastrophes. I like that. What was the book? It was called A Series of Unfortunate Events. Anyway, we are imagining, we are guessing that the universe starts off in something called the false vacuum, and that it was filled up with a scalar quantum mechanical field that obeyed a certain potential and it had negative pressure. So this was suggested back in 1979 by Alan Guth, and a few other people worked on it back then too. Now it looks like it might be actually true. If this idea is true, then the universe doubled in size about 100 times in the first 10 to the minus 32 seconds. So that was extraordinarily fast, and we call it exponential inflation, named after the phenomenon of economics. So if this is true, then what would have happened is there were quantum mechanical fluctuations in the early material. They were stretched out by this exponential expansion and then frozen into the structure of the universe. So when we went and measured the Big Bang, we measured the spots that are left over from that time. Then thank you. The vital liquid. So anyway, it is said that this wonderful imaginary inflaton field would roll and turn its energy into particles. So we now have a universe full of particles that were produced in that expansion and cooling. And there were phase transitions as antimatter reacted with the matter. As the quarks got together to make baryons, the baryons made nuclei. Nuclei met up with electrons to make atoms. These are all numerous phase transitions, and that's not all of them. And accompanying this series of cooling events is the idea that certain kinds of interactions freeze out, and the material becomes too weakly, no longer can interact directly. So the dark matter started interacting only by gravity. The neutrinos stopped bumping into things. The electrons disappeared and became atoms, so they stopped bumping into the photons of the cosmic background radiation. So we're now able to look back in time because of that and see it. So following that, we have more and more phase transitions, more and more ways in which concentrated order can produce more entropy. And this last bit, I want to say something astronomers talk about, but hardly anybody else notices. A self-gravitating system has what we can call negative specific heat. Well, negative specific heat means it heats itself up. So in your high school physics, they don't tell you that could ever happen, because it doesn't, except in gravity. So how does this happen? Well, if you have a satellite orbiting the Earth, as it feels friction from the atmosphere, it falls inwards, and it goes faster and faster. So it has converted gravitational energy into kinetic energy, and that's negative specific heat. So the universe is unstable in a whole series of different ways, and because of them, we are here. So how do we know these things? Well, I think everybody has seen Edwin Hubble's chart. This is the chart showing the expansion of the galaxies. The distant galaxies, the distance on the horizontal axis and the speed recession on the vertical axis back in 1929. So this is my example of why we don't say that astronomers are just cooking up this story. We were forced into it in 1929 by observations. Distant galaxies are going away with a speed proportional to distance. Divide the distance by the speed, you get the age of the universe, and he was wrong. 1929, his distance scale was off by about a factor of 7. So his slope there gives you an age of the universe of 2 billion years. It didn't take too long before we knew that there were things older than that. So this must have been a big problem. It just turned out to be a wrong measurement of distance. Sorry about that. It took us about 50 years to find the mistakes. Anyway, so we found out that the universe is expanding. Then in 1948, it was predicted that there should be a heat radiation left over from those earliest moments of highly compressed universe, and we should go look for it. Nobody went and looked. So it was discovered in 1965 when I was a college student. I said, everybody knows that's supposed to be there because I read it in George Gamoff's little book, but in fact it was a big surprise to the professionals. And so in 1970, I was looking for a thesis project. Okay, let's go measure that cosmic background radiation from the Big Bang. And my thesis project did not work. So what do I do then? I got a job to become a radio astronomer at NASA in New York City. And while I'm there, NASA says, let's have proposals for new satellite missions. I said, boss, my thesis project failed. We should try it in outer space. He said, we'll call up our friends, we'll write a proposal. And it actually flew 15 years later, which, by the way, is 30 years ago this month. We're having our 30th anniversary party in a couple of weeks. So amazing, amazing thing. So 30 years is an instant of time, and yet the transition of technology that it took is amazing. When I walked into NASA, we got big pieces of paper and sharp pencils to draw a satellite and build it. And then we took our drawings over to machinists who turned cranks on lathes, and now it's nothing like that anymore. Anyway, this is the instrument package that we built and sent up in 1989. It has 3 instruments in there. 2 of them are cooled by liquid helium to 1.5 Kelvin. The third instrument surrounds the central tank in 3 little boxes, and they were used also. And so presumably this equipment is still up there, but we don't talk to it anymore because it's probably dead. Anyway, as was mentioned, we measured the black-body curve, sort of. This is a measurement that shows the Big Bang has the same spectrum as a perfect black body, within 1% on this chart. Eventually, the error bars went down to 50 parts per million. So this is the result of extremely diligent calibration software from our colleagues and averaging almost a year's worth of data together to get that curve. So did we prove the universe has a black body spectrum? Yes, we did. Did we measure Planck's curve? No, we didn't. We assumed Planck was right. Anyway, it was a tremendous accomplishment. We got a standing ovation when I showed this to the astronomers a few weeks after COBE was launched, and thought, why were they cheering? Didn't they know that was the right answer? And so that's because I had a prejudice that this was the right answer, but actually we did not know that was the right answer, and there's no answer in the back of the book. This is the answer in the back of the book. So a couple of years later, we got this other chart, which was a measurement of the hot and cold spots of the early universe. And this is the one that's actually changed everything for so many people. We measured a map that was made by combining hundreds of millions of measurements and averaging down the noise, and that had to be done very carefully. Anyway, first measure the sky, then subtract the effect due to the motion of the Earth through the sky. That's a Doppler shift. Then subtract the effect of the electrons in our Milky Way galaxy, and you left the picture at the bottom, which is the whole sky compressed into an oval with little hot and cold spots that are apart in 100,000, different from the average, and the average was only 2.7 degrees Kelvin. So this was a huge technological marvel for us, and it set off an immense effort to follow up on it. When Stephen Hawking saw this chart, he said it was the most important scientific discovery of the century, if not of all time. And I didn't know why he was so enthusiastic at the time. I just thought I was really proud that we'd been able to measure it. But why is it important? Well, number one, gravity operating on the density differences in the early universe is able to stop the expansion of material locally and turn the material back around and have it fall back in to form galaxies and stars, just as I was telling you with these collapsing gas clouds. It's enough gravity to stop the expansion. Number two, most of those spots come from cosmic dark matter, which astronomers can deduce and nobody can see, but it's pretty darn sure that it's there. So that's another hugely important discovery. And number three, if we ever can figure out what made the spots in the first place, we might understand quantum gravity, and that's still in front of us. So some of you here will maybe work that out. I hope you do. So just to summarize, what is our story of the early universe? This is our standard picture. It was very hot and very compressed when it was young. It has no center and no edge. It is probably infinite. It is expanding into itself. There's not another universe for it to go into. It is just this one. Thank you. There is also not a first moment. Now, when Mr. Fred Hoyle gave us the name, when Sir Fred Hoyle gave us the name of the Big Bang Theory, it's because he did not like this theory. And so everybody has been completely misrepresenting the story ever since. You hear the word Big Bang, you think, oh, it must be like a firecracker, which happens at a place and a moment of time. And it's exactly the opposite of what cosmologists think we are seeing. We see no first moment. There's no first moment, just as there is no smallest positive number. You cannot make a smallest positive number. There's no such thing. So we don't think there's a first moment of time either. Not according to this story. Now maybe there is, but it'll have to be something based on another version of physics, and we don't know what it is yet. So this is not a big firecracker. It's not a Big Bang. Well, the Hubble Space Telescope was launched just a few months after the COBE satellite, and it is still up and running, thanks to the fact that 5 space shuttles full of astronauts have been up to visit it and upgrade it. And so it is our workhorse, astronomers' tool for measuring things way out there. So now I want to show you some of the things we got with that and talk about what we're going to do next. So here is something called the Hubble Deep Field. Astronomers decided to point the telescope in one direction for 2 weeks, and they chose that direction because there was nothing to see. No stars. Actually, there are 2 little stars in there and nothing else. And they found thousands and thousands of galaxies, and this was a big surprise. There are many, many more than they expected, and also they're much farther away and much fainter. So astronomers had predicted they would be able to see the very formation of the very first galaxies using the Hubble Space Telescope. And the answer was, sorry, we can't see them. And as soon as they got this picture, they said, please build us another more powerful telescope. We want to see the first galaxies. So that's what we're doing. So here's another story to tell you. Everybody knew when I was a college student, a graduate student, that the universe is expanding, but it must be slowing down, because the gravity of the galaxies were pulling them all back together. It must surely be slowing down. So many telescopes were built to measure the rate at which it's slowing down, but it's not. So these guys got their Nobel Prize in 2011 for showing that the universe is accelerating. And how would you know that it's accelerating? Well, you measure the brightness of stars way out there, and you say they're 20% fainter than they should be, which means they're farther away. That means something's the matter with your story. So 20% is a big deal now. We can measure quite well, so we're quite sure of this story. So, okay. And then it's been confirmed in other ways. So, okay, let's have a prize for discovering dark energy. We gave it a name that's completely wrong. Again, there's no such thing as dark. It's not energy. It's just a feature of the universe. But anyway, we call it something. So anyway, there it is, dark energy. Now I can show you a simulated formation of galaxies. If you believe the story I tell you, that we know how the universe started with random spots that are a little more dense than average, and I say galaxies are formed by gravity acting on those spots and pulling them together, I can now say, okay, supercomputer, tell me how that works, and I'll make me a movie of the formation of galaxies based on gravity and the primordial system. So here it is, gravity pulling galaxies back together from the expanding material. The computer folks have taken a box of material, they're rotating it in front of your eyes so you can see it, and they've imagined that it wasn't expanding for the purposes of the picture. So what we see is huge structures are forming, they're almost flat. There's huge streamers of material forming through space. And after about 4 billion years, things start to explode. These are black holes forming. Stuff falling into black holes will release a huge amount of energy. Bursts of stars that all happen to come of age at once blow up as supernovae. So this is a pretty rotten time to try to be alive if you're near any of those. So Earth and the solar system did not yet exist. Of course, this is not a piece of our universe. This is a piece of a hypothetical computer-generated simulation. But if in this simulation, even our universe would be, our solar system would now be forming around 9 billion years after the start of this process, when things are quieting down. So this is a reminder that the computer is a tool that enables you to see the time dependence of things in complex systems that you could never possibly deduce just by looking at a picture. Astronomers had pictures that never would have guessed this was the way it worked. So how would you know if the movie is true? We got to take pictures. So here's one picture I love. This is the Whirlpool Nebula taken by Hubble. And in the lower right corner, there's a picture drawn by an Irish astronomer, Lord Rosse, who had a 6-foot diameter telescope in 1845. But he didn't have a camera. So he had to just look and see what he could see and draw it with his, he was a pretty good artist. You can see he got the story. There is the Whirlpool Nebula. And by the way, there are 2 clouds out there, and they are about to have a collision and join to become one. Part of our story. Here's another part. This is the Hubble taking a picture of the Crab Nebula. This is a star that blew up on July the 4th of AD 1054, which we know from Chinese records, and we think we know how to read their calendar. So this is a part of our story because this is where this sort of process is where the chemical elements of life, the things that you see in this room, are ejected in space. So this particular one is not part of our history because we're looking at it now, but probably 1,000 of those blew up near the pre-solar neighborhood and contributed their chemical enrichment to what we're seeing here. The room that we're seeing is made out of the debris of things like that. What happened then? Well, that stuff gets recycled. So here is a telescope we built in South America. It's a millimeter wave telescope. The picture in the upper left shows you an image of a star that's forming a new disk of planets around it. So we're actually seeing the light that's coming out from the dust grains. So this is a remarkable picture that you're not really seeing the star, but you are seeing the dust grains. And in the dark rings, in between the bright areas, we are seeing things that are probably places where planets are being born in these little gaps. So here's a future solar system with maybe about 9 planets in it, and it's a totally astonishing thing that we could even imagine measuring it. Anyway, huge technological accomplishment there. This international team built that one in South America. So now to my favorite topic, the James Webb Telescope. Here it is in its glory, an artist's concept, of course. This is being led by Goddard Space Flight Center, where I work. It's in partnership with Europe and Canada. We have a big contractor, Northrop Grumman Aerospace Systems in California, and we have pieces from all over that are in the instrument package, with cameras, spectrographs, and fine guidance sensors from Europe, Canada, and the US. Telescope is going to be launched from French Guiana in 2021, March 2021, because the Europeans are buying the rocket. Telescope is going to be cold down to a low temperature of about 50 degrees Kelvin so that it doesn't emit much infrared. So I'm going to skip over a lot of the wonderful engineering details of it and just show you some of the things that will happen to it. So here is the sort of sequence of what it takes to get a telescope that big into space. First, we put it together in our giant clean room at Goddard in Maryland, and we put a big plastic tent over it, and we put it on a shaker, and we made to see if it would survive launch. So it's an extremely scary event when you see your favorite telescope jumping up and down, and it actually was even more scary because it made a noise that it wasn't supposed to make. So we said we better stop now until we figure this out. So we've made a design change, and we kept on going without breaking it, which was really important. So after that, we put it in a shipping container, send it around the highway to Andrews Air Force Base in Maryland, put it in the airplane. This is called a C-5C airplane. It's just so big that you can put the entire truck in along with the telescope, fly it down to Houston, Texas, take it back out again and put it in the giant vacuum tank in Houston that I told you about before. Cool it down to the flight temperature of about 40 Kelvin, make sure it still works, does all of its everything. Then put it back in the airplane, take it to California, and have it meet up with the rest of the observatory, which is a warm spacecraft and a giant umbrella called a sunshade. Put it together, make sure it folds and unfolds, vibrate it again, and make sure it's all done with surviving launch. Then put it in another shipping container, put it on a boat, send it through the Panama Canal, and take it to French Guiana and put it on the rocket. This is a European rocket called the Ariane. They have had, I think, 75 good ones in a row, which is good as rockets go. And so odds are high for us. We push the button. It takes about a month to get almost all the way to the launch point, L2, where we're going. And then we spend altogether 6 months getting it all set up and working before we say, okay, now we'll do astronomy. So that's our plan with this great observatory. Now I show you our scary movie. This takes about 2 weeks to do this. First, we unfold the solar panels, and the antenna that talks back to Earth. Then after a while, we unfold the structure that holds up the sunshade. And then I say, look at this picture, isn't this astonishingly complex? And isn't that kind of scary? And the answer is yes, both. And on the other hand, as far as we know, this is the only way to get the scientific answers that we're after, to be able to see those very first galaxies that the astronomers were asking for. This is all done by remote control. There's no human being anywhere near, so it means we have to get it right. So here we are doing one of the more delicate things. We're separating the 5 layers of the big umbrella, big sunshade, so that they will work better. And this is all done by winding up cables. A sort of standard technology, but every version is different, so this has been making us nervous. The last step is unfold the telescope. And now it's almost the right shape, but not quite, and it's cold. It's not cold yet. I have to wait for it to cool down to the operating temperature. Then all of those 18 golden hexagons have to be put in the right place by focusing with a special algorithm that we invented. And by the way, that's the result of having failed with a Hubble Space Telescope. It was launched out of focus. We had to measure and figure it out, and so we did. And now we can do it on purpose. So how good is it going to be? Well, the benefits for us? Well, it is going to be extraordinarily powerful. If you were a bumblebee, that is to say 1 square centimeter, at the distance of the moon away from the telescope, we would be able to see you. So how can it be so powerful and so everything? Well, number 1, it's very large. Number 2, it's very cold. And number 3, the detectors are extraordinarily near perfect. So it's totally overwhelming to imagine the power of this piece of equipment. The hard part for us is to look at bright things like Mars, so we have to take very quick exposures to be able to do anything at all on Mars, but of course we figured that out. We will also be able to watch very bright stars because once in a while a planet goes in front of them and we want to be able to see that. So I showed you earlier a picture of this beautiful nebula where stars are being born today. What you see here is glowing clouds of gas and deep dark clouds of dust protecting those new stars from our sight. So you cannot actually see the new stars being born in there because they're surrounded by dust grains. But if you use longer wavelength, you can see around the dust grains. So dust obscures light that is of comparable wavelength to the size of the dust, but if the wavelengths are longer, the dust does not stop it, and you can see inside. So this is like when you go to the airport and they see through your clothes with your millimeter wave equipment and to see if you're carrying bad things on board the airplane. This is the shorter wavelength version of that, seeing inside the dust clouds, the stars being born. What else will we do? We'll look at everything else. One remarkable thing is we can look at these things in the solar system. Europa is a satellite of Jupiter where we imagine that we will be able to see signs of life if there are any. We know there's an ocean out there. It's covered with ice, and once in a while there are little geysers of water that is spurting out from this little moon. So long-term future, we would like to land a probe over there. The near-term plan is let's go build something that flies through the spouts, flies through the geysers to see if there's what's in that water that's coming out of the Europa. So long time ago we flew that mission out there, but we still know it's a very exciting spot. And by the way, this is one that congressmen like, so that's why we're going there. They like it too. So what else will we do? We'll be looking at stars that blink, stars that have planets that go in front of them. Some of you noticed that Mercury went in front of the sun this week, and it just blinks a very tiny amount. But we actually have thousands and thousands of planets that have been found in this fashion, so we will be able to follow up some of them. The remarkable thing for planets seen in this way is some of the light from the star goes through the atmosphere of the planet on its way to the telescope. We can analyze that, get its spectrum, and determine what is the chemistry of the atmosphere of a planet around another star. We already know we can do this, and we have a pretty good list of targets already. So we'll be trying. I don't know if we're going to be able to see water out there on another planet, but we're certainly going to look. What else would we do? Well, here's the big question a lot of people have. Is Earth special? I think it is. I like Earth, but there are reasons to think that although planets are very common, most stars have planets, we have not seen any that are like Earth yet. And so why is that? Don't know really. But Earth is special for us. It's the right temperature to have an ocean. It's got a nice orbit, stable and circular. Has a very big moon relative to the Earth. Has a big magnetic field that protects us from the solar cosmic rays. It's got just enough water to cover up part of the land and have something dry to live on. Got the right amount of carbon and nitrogen for us. It's a good star. It's not too dangerous. It's not near other black holes and so forth. And this last one might be important, and we would like to know about other planets around other stars, whether they have any sign of this. We have plate tectonics. The surface is moving around, and it is thought possible that that's the place where life may have originated down there in deep undersea vents. So, pretty interesting question. It is too soon to answer this question, but this is one of the hottest topics of astrophysics today. What are the planets like way out there? So I want to show you a couple of things astronomers are working on before I wrap up. Number one, we're building some really gigantic telescopes on the ground already. There's a 24-meter telescope, which is 4 times as big as the Webb telescope, a 30-meter telescope, 5 times as big, and finally the biggest one, the 39-meter telescope, which is quite well along in Chile, and that's European project, 39 meters, enormously powerful equipment. And we need something that we are working on called adaptive optics. So back in 1953, an astronomer said, gee, I wish I could have adaptive optics because it would compensate for this turbulent air that I have to look through. I get a blurry picture when I try to look at a star. So we now have it. It was first developed for weaponry because the military said, we want that too. And as soon as it was started, the military classified it. It was work that was started in Berkeley when I was a graduate student. Anyway, it was reinvented about 20 years later by French astronomers, and now you can't classify it anymore. So astronomers have it, and the right-hand picture tells you that eye doctors have it too. So one of the people who figured out how to make the mirrors for the Webb telescope also figured out how to make this right-hand diagram. So when you go to your eye doctor, his equipment is now used so the doctor can see what's going on inside your eye and tell you how healthy you are. And in addition, if you say, I want to see better, doctor, they can tell you exactly what to do with their laser surgery so you can get 20/10 vision, much better than your natural eyesight. So who knew that we would have millions of people benefiting from adaptive optics in your doctor's offices every day? So you ask, what is the benefit of space astronomy? Well, I couldn't tell you in advance, but this is one. Now, I want to show you one last idea that I'm working on personally. I said, well, there's another way you could see planets around other stars. You could cast a shadow onto your telescope. And this is not the first time that's been thought about, but how about we use the telescopes we're building on the ground, which are enormous, and put up something orbiting in space and cast a shadow from space onto the telescope on the ground. So you have to put it pretty far away, about 170,000 kilometers. And you have to have the velocity match the velocity of the telescope. And then if you do this, you can take a picture of a solar system 5 parsecs away, that's about 16 light years, and get a picture of an Earth in a minute. So if you could do this, it would be pretty spectacular. And I'm now trying to get this project idea filled out. Are we going to do it? I have no idea. I think it's interesting. So I think this is my last topic. People want to know, well, how far can you go into space? And the answer is not very far, darn it. We can send robots as far as you like. Have already sent them to asteroids, comets, all the solar system objects, some dwarf planets like Pluto. Pluto was very upset when we called him a dwarf, but he has more friends now because of that. Anyway, computers are getting better all the time, and they can beat us at anything, practically. And an interesting question for our social world, well, who owns them and controls them, because they're weapons as well as tools. As far as where can we go, well, people are very fragile. We do not like cosmic rays. We do not like getting killed by cosmic rays in space. We know that mice exposed to the full cosmic ray damage lose their minds after a little while. So we're going to have to protect ourselves from those cosmic rays if we want to go traveling very far. Robots can be built to be much more tolerant of those things. They don't have to breathe, and they can survive cosmic rays. So they're going to be going. If they have their own minds by the time that we're talking about this, they could say they want to go visit the other planets. They could even say, gee, boss robot, I want to go visit Alpha Centauri and see what the planets are like over there. But even they will have to be very patient because it's a heck of a long trip. So I don't think we're going to have Star Wars. We're not going to have Space Odyssey. It's probably all still fiction. But can I prove that? No. Maybe it's not fiction. So maybe time for questions. Thank you very much. Okay, thank you.
Okay, so we're going to have people out in the audience.
Huh? Okay.
So time for questions. We have people out in the audience. If you have a question, please raise your hand, and somebody with a microphone will approach. Oh, Steve Feller over there on the left-hand side.
Hello, thank you for your talk. Oh, goodness.
Move away from the speaker, please. Walk away.
All right, thank you for your talk. Which application of the James Webb Telescope are you most excited for?
Oh, golly. I think what I'm most excited for is the possibility that there's something out there that nobody ever guessed was there. So I'm looking for the surprise. We have a big plan. We've already decided what to spend the first roughly 6 months of observations on. We've got a long list, well reasoned. Everybody has a good reason to look over there. And I'm hoping there's something that nobody expected. So we're going to look at basically everything. Everything from the first galaxies and the first quasars and the first black holes to things in our own solar system to see how does it look in the infrared. I didn't tell you much about the instrumentation, but it covers the infrared band from 0.6 microns to 28 microns. So a little bit of visible light, a lot of infrared, and a very different phenomena than what you can see with the Hubble telescope.
Hi, thank you so much for such an excellent talk. I just wanted to ask you about nuclear pulse propulsion and what you think about that, and if it has any grounds in the future or not.
So nuclear pulse propulsion, I guess you're thinking about where you put off a nuclear bomb behind you and let it push you. Is that one? Anyway, it sounds pretty dangerous to me, but it was taken quite seriously a long time ago because we know how to do that. So in principle, you can do it, but I don't think anybody much likes it right now.
That was very inspiring. Thank you so much. So I was wondering, as an astrophysicist, what's your view on pop culture, such as movies and books misusing physics concepts like quantum theory, dark matter, and parsecs? Do you consider this as a problem, and what can be done to resolve this if you think it is a problem?
Well, the conflict between quantum and relativity is a fundamental issue that I don't know how to solve. And I'm thinking somebody here will do that. So it's beyond me to tell what the answer is going to be. I love string theory, what I've heard about it. I can't work on it myself. It is beyond me to take all those Lagrangians and do all the algebra and the math to turn that into an understanding. But anyway, I think string theory has something going for it, but it's turned out to be a lot harder than people thought. I don't think I answered your question.
Hi, I really enjoyed your talk. It was mind-blowing. My question, since you did mention about the transit photometry and using it to study planetary atmospheres, do you think that the Webb telescope has instrumentation capabilities of direct imaging exoplanetary systems, or even using it to study things like the composition of the planets themselves?
So the question is, can you see them directly? The answer is, if they're big and bright and far from their star. We did not intend it for that purpose. When we started off, we knew that was almost impossible to do, but we know that Hubble can do a few, and we've seen a few with the Hubble with the direct imaging, so we'll just try those and others, and we'll try it. We'll tell you what we see. It depends on whether those planets are big and bright. Like the stars in Texas, right?
Like the stars in Texas.
Hi, fantastic talk. Thank you very much. When you were talking, you were mentioning with the transport of the satellite through all of the different test facilities. It sounded like it was a lot of packing up, transporting, unpacking, facility, packing up, etc. What happens if it gets damaged along the way? Does it set it back a few steps, or does it have to be fixed on site?
I don't want to know about that. So we've taken every possible precaution to make sure it won't get damaged on site. We have one more trip to do. We have to get it on the boat and through the Panama Canal. So we won't go with the weather is bad. We will hide out somewhere if the weather is going to be bad. So we know that's the big worry that we have there is bad weather. But a boat ride is pretty gentle most of the time. It might make you seasick, but it's not very dangerous for a telescope.
Hi, thank you for the talk. I was just wondering why it takes so long to unfold the James Webb Space Telescope once it's in space.
Well, it doesn't really take very long, it's just we're cautious. So because we are not there in person, we can't witness it, so we have to depend on instrumentation to tell us whether everything is working. So we do a little bit, check a little bit, do a little bit more, check some more. And if something hasn't worked, then we try the other way. Everything that we can make redundant has two of everything. So if the first way to do something doesn't work, try the other way. So we have to have time to make sure everything has been accomplished before we go to the next step. So that's just the unfolding part, a couple of weeks. The longer part is making sure all of the instruments are set up and the telescope is focused. So there are roughly 1,000 different procedures to follow to make that happen. So a lot of human effort involved.
Thank you so much for the talk. I do have a question. Could we make a comparison shot of what the Hubble deep sky photo is with the new James Webb?
So we think that the deep picture that Hubble took, well, we can do it about in a couple of hours as compared to 2 weeks for the wavelengths that we both can see. That's pretty good improvement in power. And then, of course, we go up to much longer wavelengths where the Hubble couldn't see anything. So the primary motivation for this new telescope was to go beyond what Hubble could see. So the Hubble can see out to about 1.7 microns wavelength, and then they just stop. And that's because the Hubble is warm and it glows and emits infrared very powerfully at longer wavelengths. So the real big advantage of the new telescope starts there and goes on to longer wavelengths. So we think we know what we'll see, and we might not.
Hi, I don't have a super interesting question, but thank you so much for this. It was incredibly fascinating. I'm really excited to see where the Webb telescope goes, but there was a lot of really amazing media that you put up here. Is there any way we could get the citations for that so we could explore a little bit more on our own? The media, like the videos and things, you can find those by searching on the internet already. We have an archive at NASA where we post all these videos. I think we got a Flickr site, we've got a media site at NASA, and yes, we can get you the information to you.
Hi, thank you. We learned from Einstein and Edison that massive bodies warp light, and we learned from the Hubble telescope that if you look in any direction, you'll encounter a massive body. So do you think the gravitational lensing effect has any notable effect on the picture we took of the cosmic background radiation, or no?
Answer is yes, we know that it has a big effect, but only on very small scales. It wouldn't affect the picture I showed you, because that's a big fuzzy picture, but the typical light beam from the Big Bang material to now has been bent by about 2 arc minutes on the way from there to here by the gravitational interactions along the way. That's a lot. That's comparable to the resolution of your eye. So when you get a sharp enough picture of those Big Bang fluctuations, you can definitely see a statistical effect. Of course, you do not know what it was supposed to be, but you can get the statistics and calculate where the stuff is.
You said that the universe is accelerating, and I know there are some theories out there that say the universe is going to accelerate past the speed of light, so where we aren't going to be able to see it anymore. So do you think that theory is going to happen? And if so, how long will it take to happen? And thank you for your talk.
Okay, so we are, according to us, the distant universe already, most of it is invisible to us. The part that we can see, well, light has been traveling 13.8 billion years, so that's a certain distance. We imagine that material has now moved a little farther away since the light was sent to us, so that's about 45 billion light years. And then we say, well, there must be an awful lot more universe beyond that. So most of it's already invisible to us, because the universe is not old enough for the light to get here. And now we say, and by the way, since it's accelerating, it's never going to get here. So according to prediction, if the acceleration continues, after a while, almost all of the galaxies that you know of are going to be stretched away so you can't see them. And then we'll just be left with our own Milky Way all by itself saying, where is everybody? But that's not for a while yet. And those people would never have a clue that there was a Big Bang either, because the microwave background radiation would also be gone by then.
When the Hubble telescope was released and there was that unfortunate disfocus, we had the chance to go up and fix it. How are the risks similar and different for the James Webb telescope?
Okay. Well, the risks are obviously large that if something's wrong, you can't fix it. We do not have now or in the past when we were planning any obvious hope of going up to visit it in person. But we are now building at last the great rocket, the SLS, the Space Launch System, and a capsule to go on it. So in principle, if we really cared, we could go out there in person, not right away. And we also realized that maybe we would send a robot. So we were actually doing what's necessary, painting a pattern that the robot camera would know about on the warm end of the telescope, so you'd be able to latch on robotically. Then what you do when you get there, that's a whole other story. We hope there's nothing to do. But at least we know that we could go out and attach. So our main job is to make sure we never need to go.
So you mentioned the screen, the sunscreen, to cast a shadow down onto the Earth. I know that keeping things at a distance away from the Earth in some sort of orbit is difficult. What are the odds that something like that would either be flung away from the Earth or towards the Earth? And if it were to fall back towards Earth, what effect would it have when it got close?
Okay, well, if somebody said go ahead and build it, the orbit you would choose would be a safe orbit, so it's never going to come back. But you do have the need to maneuver it quite a lot because each different target star needs a different orbit. So we'd have a lot of rocket thrust on board to make sure you could do that. So our job is to make sure nothing bad happens. Something that big is going to be more like a sail than a piece of glass. If the Hubble telescope were allowed to fall into the Earth, that piece of mirror would come right straight through in one piece, and then it would hit something. So that's one of the reasons we can't allow that to happen. The star shade probably would fall apart into little bits.
Hi, it was such a nice talk, Dr. Mather. It's such a pleasure to see you. My first question actually is something I've had for years, and it concerns the star shade. You were talking about how the star shade is really big and it's placed very far distance from the telescope. And I guess I was wondering, what difference is there between a really big star shade that's far away and a smaller one that's closer by that has the same angular width?
Okay, the difference is about diffraction. So people need to appreciate how hard a problem this is. If you were to put a circular star shade way out there, it would cast a shadow with a bright spot in the middle. How many people remember Arago's spot or Poisson's spot? Anyway, the diffracted light that goes around a circular object will all add up at the middle of the shadow and it'll suddenly be very bright. So you have to shape it. That's why the sun shade has all these pointed petals. And then you have to put it far enough away so that the diffraction of light is also not a problem. So that tells you the sort of minimum distance. In our case, the minimum distance is set by the orbit. If you get it any closer, it'll hit the Earth. And so that's the reason that one is like that. If you were in space, you could have it a lot closer and it would work just as fine. Yeah.
Do you have a prediction for the lifespan of the James Webb Telescope?
Yeah, we're carrying a fuel for 10 years of scientific operation. If we have a good launch and the rocket puts us in the right place, it could be a lot more. If we have a bad launch, it could be less. But anyway, it's aimed for at least 10 years. And who knows? It's a matter of luck and whether we did a good job with the design, whether it lasts the full length. Hubble is lasting a long time now, but it's now the 5th time we upgraded it. So we got better.
Hi, thank you so much for your talk. My question is, what were the thoughts and emotions that were going through your head when you first saw the Hubble Deep Space Field image for the first time?
I wasn't paying enough attention at the time because I was still thinking about Kobe. But it didn't take too long for people to get my attention that this was obviously a huge accomplishment. The recognition that it still didn't answer astronomers' prayers, that took a little longer. But I do remember, this is slightly a different story, when the Hubble had just been repaired for the first time, the internet crashed because everybody wanted the picture that we had just taken. And the internet wasn't able to handle the total demand for Hubble pictures that day.
Time for two more.
Two more questions.
Then a couple of star-shaped questions. I'm intrigued by the mission that you've got working with the extra-large observatories on Earth. I'm wondering, what are the advantages of doing this in space versus doing this on the ground, doing a joint formation star-shaped fly, for example?
Okay. So the advantage of doing it on the ground is you have a bigger telescope and you're already building the telescope. The advantage of doing it in space is there's no air out there and you don't have to do it nearly as well. You have a much more forgiving environment for the telescope. So you don't need adaptive optics in space. And if you're very good at building your telescope, you don't have to have a star shade. You can build a perfect telescope and adjust it very, very, very carefully so that you can get rid of the starlight and still see the planet. It's a piece of equipment called a coronagraph, and it's possible to do. It's pretty hard engineering, so we don't know which way we're going to go. By the way, just to tell you a story how we make up these decisions, every 10 years, the astronomers get together and they have what I call a science party, which means we write a book about our priorities. So this is sponsored by the National Academy of Sciences, and they write this little book and they say, this is what we think is the coolest thing to do in the next 10 years. And astronomers have their fights, and then they say, okay, let's do this. And Congress says okay, and NASA says okay, and so we go do it. And usually it takes longer than 10 years. Okay, last question.
Hi, I was wondering if you could talk a little bit about the initial design process for something as large and complex as James Webb. So, like, how much was it based off of Hubble, and how much did y'all just design from nothing?
Oh, well, it's a very long, involved process. First, John Mathers draws a sketch, and everybody says, no, that's not right. Let's draw a different sketch. And after a little while, we say, well, this isn't so ridiculous after all. Let's go talk to more people. So we held a conference, and we briefed our potential industry partners that might build such a thing. And they said, well, that's interesting, but we don't like your idea. What we want you to do is sponsor a competition. So we did that. We ran a competition. And so industries formed teams with university scientists, and they wrote us proposals. And they had some rather different ideas about how to do this. So that worked for a while, and then we said, okay, now we think we understand well enough. We'll keep on going ahead. We'll figure out what to do next. And then quite a few years later, about 6 years later, we had another competition. And actually, these are bids from big companies. We will build your telescope like this. And this is our idea, and this is why we're the best. And so we spent about a year reading proposals to say, well, we choose you and not you. And so there were different design concepts inside, different ways of folding the telescope, but basically they both could have worked. And we just had to say, well, we think this one will be better for some reason. So it's not John Mather draws it on the sketch. It's never like that at all. It's very, very thorough engineering studies are done to say, we think this is the right answer because.
Round of applause.
Yeah, thank you.
All right, everybody, we just wanted to thank Dr. John Mather one more time on behalf of Society of Physics students at Sigma Pi Sigma. We want to present him this gift. Thank you. Give it up.
Thank you. Thank you. Thank you. Thank you. Okay.
Thank you. Take your seat, please.
Okay.
Thank you. Appreciate it.